Introduction. Scottish scientist James Clerk Maxwell developed a concept of electromagnetism, which is one of the greatest discoveries of the 20th century. He assembled a set of equations that is known as the Maxwell equation. There are four Maxwell equations. The first and second Maxwell equation are referring to Gauss' law, but in different type of field, which are electric field and magnetic field, respectively. The third Maxwell equation is Faraday's law, whilst the fourth Maxwell equation is Ampere's law. Gauss' law in terms of electric field is the first Maxwell equation. It states that the electric flux through a closed surface is proportional to the total charge enclosed by that surface. The equation for this Gauss' law is simply the integral of electric field over the area of surface, which is equal to the enclosed charge divided by the permittivity of free space. Let us proceed to a second Maxwell equation, which is a formal way of saying that monopole magnetic source does not exist. Equation states that the divergence of the magnetic field and magnetic flux is zero through any volume, since both of them are related by the permeability. Away from the magnetic dipoles, magnetic field flows in a closed loops. This is true even for plane waves, which just so happen to have infinite radius loop. What do you understand about this experiment? Yes, that's right. It's related with Faraday's law. Faraday's law is the third Maxwell equation, and it states that induced electromotive force in any closed circuit is equal to the time rate of change of the magnetic flux linkage by the circuit. As stated before, this is the equation for the Faraday's law of induction. Oh, and don't worry about the negative part because it is just part of the Lenz's law. The second equation, which Maxwell came up, is similar to the first equation, yet much simpler and general. The equation states that the integral of electric field with the infinitesimal of closed loops is equal to the negative of change in magnetic flux over the change in time. The last equation which completed Maxwell equation is Ampere's law, which states that in integral form, the magnetic field induced around any closed loop is proportional to the electric current plus displacement current. For any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop. After knowing the equation, Maxwell has to consider a situation where the flow of current doesn't induce magnetic field. Therefore, he added a displacement current to complete the equation. The displacement current is proportional to the rate change of electric flux through enclosed surface.
Maxwell equation in final form. Maxwell equations, four equations that together form a complete description of the production and the interrelation of electric and magnetic fields. This Maxwell equation is introduced by James Clerk Maxwell with his description of electromagnetic fields on these four equations, which express experimental law. The statement of these four equations are respectively: Number 1. Electric field diverges from the electric charge, an expression of the Coulomb force, the Maxwell that corresponding to the statement divergence D equals to rho. It is derived from the Gauss's law. 2. There are no isolated magnetic poles, but the Coulomb force acts between the poles of a magnet. It corresponding to the statement of B equal to 0, and it derived from non-existence of magnetic monopole. Electric fields are produced by changing magnetic field, an expression of Faraday's of induction. This Maxwell all correspond to the statement of curl E that derived from Faraday's law. Number 4. Circulating magnetic fields are produced by changing electric fields and by electric currents. Maxwell extension of Ampere's law to include the interaction of changing fields. The Maxwell correspond to the statement of curl H that derived from Ampere's law. Last but not least, here is the summary of Maxwell equation in the form of differential and integral forms.
Application of Maxwell equation. Magnetic resonance imaging. Magnetic resonance imaging (MRI) is a type of scan that uses strong magnetic fields and radio waves to produce detailed image of inside of the body. MRI scanner is a large tube that contains powerful magnet that can be used to examine almost any part of the body. During the scan, magnet inside the machine will create a strong magnetic field. Proton particles inside hydrogen atom of human body are like tiny magnet and are very sensitive to magnetic field. Proton spin will create a magnetic charge. When a strong magnetic field is introduced, proton will align with that field. Then, the scanner will send radio wave to the body. This will disrupt the proton and force it to 90-degree or 180-degree realignment with the static magnetic field. When the radio wave turned off, proton realign with the magnetic field and release electromagnetic energy. Then, the scanner will pick up the energy signal from the body and use it to make the pictures. A key point of Maxwell's equation is that time-varying magnetic field gives us a rise to electric field or vice versa. This is the basis of detection of MRI signal. MRI also obeys Faraday's law when the time-varying magnetic field associated with the precessing magnetization in MRI induce voltage, giving a rise to the MRI signal. Conclusion. The vast knowledge of electromagnetism that we have today are the doors it has opened into the field of relativity and quantum theory are all based on the theories that Maxwell and his predecessors developed.